Next, we look at the rotational counterpart of mass, moment of inertia. When an object moves in a straight line, mass comes into effect, as you have seen in the topics of force and motion, work and energy, and impulse and momentum. Mass may be seen as a measure of inertia, in this case, linear inertia. When an object moves in a circle or when an object moves in a rotational motion, that is to say, when the object is undergoing angular motion, the rotational counterpart of mass comes into play. The rotational counterpart of mass or rotational inertia is referred to as the moment of inertia of the object. So let's consider an object moving in a circle of radius r. The object is moving, it has velocity v or speed v, in which case it has kinetic energy. Kinetic energy is 1/2 mv squared. Now, the velocity or the speed, as you can see in the figure, is perpendicular to the radius, which means it is tangential velocity or tangential speed. Angular speed, you will recall, is related to tangential speed. Angular speed omega is equal to tangential speed v divided by radius r. Therefore, v is equal to r omega, and replacing v by r omega, kinetic energy now becomes equal to 1/2 mr squared omega squared. If we let I, moment of inertia, be equal to mr squared, our equation for kinetic energy becomes 1/2 I omega squared. Rotational kinetic energy. If you compare this with our equation for kinetic energy, 1/2 mv squared, 1/2 inertia times square of speed, which means our rotational kinetic energy is equal to 1/2 times rotational inertia times square of angular speed. The unit for moment of inertia is kilogram meter squared. Just like mass, moment of inertia is additive. That is to say, total moment of inertia is summation of individual moments of inertia. I total is equal to I1 plus I2 plus I3. Now, please take note that I is equal to mr squared. This equation of moment of inertia is applicable only for an object that is moving in a circle of radius r. As it turns out, moment of inertia depends upon the location of the center of rotation or the axis of rotation of the object. Here we have some sample situations or sample objects rotating about their respective axis of rotation. As you can see, each situation, you have a different equation for the moment of inertia. For example, if we look at the hoop or ring, a hoop that is rotating about its symmetry axis or rotating about an axis of rotation that is passing through its center, the moment of inertia is I is equal to mr squared, where m is mass of the hoop and r is the radius of the ring or hoop. So I is equal to mr squared. But if we now let the axis of rotation be along the diameter of the hoop, the moment of inertia equation becomes 1/2 mr squared. So each situation, you have a different equation for moment of inertia. Now, these are just some sample equations or situations, and I leave it up to you to look for other equations in different textbooks and sources. You can also use the parallel axis theorem to determine the moment of inertia of an object. The parallel axis theorem uses the center of mass of the object. Center of mass of an object is basically the point at which the mass of the object is considered to be concentrated, at least as far as motion is concerned. For a regularly shaped object with uniform mass distribution, the center of mass is located at the geometric center of the object. Now, if you have an axis of rotation that is parallel to an axis that is passing through the center of mass of the object, you can use the parallel axis theorem as long as you know the equation for the moment of inertia of the object for the axis passing through the center of mass of the object, the ICOM. If you know ICOM, you can use the parallel axis theorem. I is equal to ICOM plus MH squared. M is the mass of the object. ICOM is the equation or value for the moment of inertia when the axis of rotation is located at the center of mass of the object. And H is the distance between the axis of rotation at the center of mass of the object and the actual axis of rotation of the object. As you can see, the two axes of rotation lines are parallel to each other, hence the name parallel axis theorem. And that's it for our discussion on moment of inertia. Again, when you see the object is moving in a circle or the object is rotating, the object is undergoing angular motion, use moment of inertia instead of mass.